Okay, so now that we know a little bit about the basics of aldehydes and ketones, let's go a little further into this chapter, learn a little bit more about these amazing substances. In this lecture, we'll specifically focus on physical properties of aldehydes and ketones. So we looked at the physical properties of the alkanes, alkenes, alkynes, alcohols, so on and so forth. So now it's the time for the discussion of aldehydes and ketones with respect to physical properties. All right, so while we had the hydroxyl group in the alcohols that allowed for us to be a hydrogen bond donor and acceptor, and therefore had unusual physical properties such as extremely high melting point, boiling point compared to things like ethers. Here with the aldehydes and ketones, of course, the polar carbonyl group is going to be our key feature, and it does have a dipole. There's the partial positive at the carbon end of things, partial negative at the oxygen end. The oxygen is more electronegative. It withdraws electron density toward itself within that double bond, and therefore it builds up a slight partial negative charge, giving the carbon a slight partial positive charge, and they can align as a result because a neighboring ketone or aldehyde would be attracted. Its partial negative and its oxygen of the carbonyl would be attracted to a neighboring carbon, which has a partial positive, and so on and so forth. So that ability to attract neighbors, again, will cause us to have maybe slightly higher boiling points than we otherwise would expect for substances like aldehydes and ketones. Okay, so as we said, we have these dipole-dipole interactions between these polar groups, these carbonyls. So the neighbors align to have one partial positive on one neighbor, align well with a partial negative on the other, and so on and so forth. As a result, we see higher boiling points than alkanes and ethers of similar mass because those substances don't have significant dipole-dipole interactions, just temporary dipoles, London or dispersion forces as they're called. However, because we can't do full-on hydrogen bonding among other aldehydes and ketones, we do have lower boiling points than alcohols of similar mass because the alcohols can form hydrogen bonds with their neighbor alcohol molecules. Here, while we do get dipole-dipole attractions, which are significant, we don't form hydrogen bonds, which are that strongest intermolecular force that we discussed back in General Organic Biochem 1. Here we see a list to give a comparison of these boiling points among substances that are roughly the same molar mass. So butane, again, it's an alkane, straight chain alkane. London or dispersion forces are all we really have in intermolecular force attractions. So butane itself, molar mass 58, family alkane, its boiling point's right at 0 degrees Celsius. If we look at the aldehyde propanal, it also has a molar mass of 58. It's the family it belongs to is aldehydes, of course, and its boiling point is significantly higher at 49 degrees Celsius. If we look at propanone, now we have the ketone, and its boiling point is even higher yet, although its molar mass is roughly the same as the others that we've discussed so far. And then finally, 1-propanol, which has a slightly higher molar mass, but not nearly a high enough molar mass to explain this difference because it's an alcohol and because it can do hydrogen bonding. That's what explains that difference between 56 degrees C for the boiling point of propanone and 97 degrees C for the boiling point of alcohol, in this case 1-propanol. So there we have it, roughly the same molar mass. So really it's down to those sorts of interactions. The alkane can only do the London or dispersion forces, whereas the aldehydes and ketones are dipoles, and they can do dipole-dipole interactions as well. And then finally the alcohol, which can undergo true hydrogen bonding, gets a higher boiling point yet. Okay, so because we do have that dipole in aldehydes and ketones, we do get some water solubility, especially if we're small. If we're 1 to 4 carbons for our aldehyde or ketone, we would expect to be soluble in water. If we go to 5 or more carbons, then we're not very soluble in water. The reason those smaller ones can be soluble is they can form hydrogen bonds with water between the carbonyl oxygen, those lone pairs on that carbonyl oxygen, and the hydrogen atoms of the water. However, when we get too many carbons, and it seems to be 5 or so is that magic number, so to speak, where we get a large enough nonpolar carbon group that we can't overcompensate with those hydrogen bonds, at least the fact that the aldehyde or ketone could be a hydrogen bond acceptor. It's not as significant as the fact that those nonpolar hydrocarbon groups want to be together. So once we get to 5 carbons, that tendency for the hydrocarbon portion of the molecules to want to interact with other hydrocarbon portions of other molecules seems to win out, and we no longer have the water solubility we have with the smaller 1 to 4 carbon aldehydes and ketones. So here we see a table from our text, table 14.1, where we get the boiling points and solubility of select aldehydes and ketones. So notice methanal, or formaldehyde as it's commonly known, it's a 1-carbon aldehyde. It has a relatively low boiling point of minus 21 degrees Celsius, but it has good water solubility, so it's usually a solution of formaldehyde, or formalin as it's called in solution, that is used as a fixative in biology to preserve, I should say, cells and tissues. Because it's water soluble, it does a nice job of forming that water-based solution. Otherwise, it's a gas, as you can tell by that boiling point of minus 21 degrees Celsius. It would be a gas at room temperature and pressure. If we move up a bit to a 2-carbon ethanal or acetaldehyde, now we see the boiling points increase significantly to positive 21 degrees Celsius, but because it's just 2 carbons, it also remains soluble in water. As we go up, we see the boiling point also increases, and the solubility stays good in water up until pentanal, where we hit that 5-carbon threshold. Pentanal, a 5-carbon aldehyde, has a high boiling point, right, higher than the 4-carbon aldehyde, but only slight solubility in water. Likewise, the 5-carbon ketone, 2-pentanone, also has a higher boiling point than the 4-carbon ketone butanone, but lower water solubility. Finally, once we hit 6 carbons for either the aldehyde, hexanal, or the ketone, 2-hexanone, we see essentially no water solubility, although we do continue to get higher boiling points because we still have just the 1 aldehyde or 1 ketone in each of these substances, but that nonpolar portion that we've said only has London forces, well, when that gets large, although the London forces are small on a per interaction basis, as we get a long tail like we start to get with these longer aldehyde ketone hydrocarbon ends, those small energy interactions start to be significant when they're spread out over 6 or so carbons. All right, so let's go ahead and pause here for some learning checks. In this first learning check, you're asked to select the compound in each pair that would have the higher boiling point, and then explain your reasoning as to why you selected the compound that you did. So go ahead, make your selection for each of the pairs, A, B, and C, and then give a brief rationale as to why you selected the molecule you did. Pause the video here while you make those assignments, and then start it back up when you're ready to check your work. Good luck. Okay, so in our first pairing, hopefully you selected the alcohol because the alcohol can form hydrogen bonds, whereas the alkane could not. For the second pair, hopefully you selected the ketone because it had the dipole-dipole interactions possible between those carbonyl groups of neighbors, whereas the alkane did not. And then finally, C might have been a little trickier because we had 2 options with the oxygen as part of a functional group. It was either the alcohol or the ether, and hopefully you selected that alcohol because the alcohol can form hydrogen bonds. Same reasoning as A, but in this case you weren't comparing it with an alkane, you were comparing it with an ether, which again, like the carbonyl groups of the aldehydes and ketones, the oxygen of the ether does have lone pairs. It can be a hydrogen bond acceptor, but it can't be a hydrogen bond donor and acceptor as the alcohols can. So we expect higher boiling points in the alcohols than any other functional group so far. All right, let's have one more learning check before we leave this section of chapter 14. In this learning check, you're asked to indicate if each of the following is or is not soluble in water. So go ahead and just assign for A, B, C, D, either soluble or not soluble. Okay, for A, it's a 3-carbon hydrocarbon. Again, it has no functional group and no reason to be soluble in water, so hopefully you selected not soluble in water there. For B, we have an alcohol, and the alcohols, especially the small alcohols like this, ethanol, the alcohol those of us who are of age may choose to consume, is quite soluble in water because it's small, fewer than 5 carbons, and it's an alcohol. For C, now we have a relatively small aldehyde, right? 4 carbons. So we said 4 carbons or less would be soluble. 5 or more. 5 actually is slightly soluble. It's sort of the changing point, and then 6 or more become insoluble. So we were at the 4, which was below 5, and therefore soluble in water. Finally, D, it's a 3-carbon ketone, and just like the aldehyde above, it's a ketone that's less than 5 carbons, and therefore we expect it to be soluble in water. So hopefully those learning checks went well, the physical properties are making sense, and especially since we're linking them back to the aldehydes, we're linking the aldehydes and ketones back to alcohols and hydrocarbons from earlier. Hopefully it's really coming together for you. If that is not the case, then please do try some additional practice problems and reach out to me for some guidance if necessary. Otherwise, if things are going smoothly, then I'll see you in the next section of Chapter 14.